Start the recording. And we were talking about forces, applications of Newton's laws, because forces cause accelerations. And that was the material of chapter 4 and 5. Now we've moved into chapter 6 today. And chapter 6 shifts gears on the motion a little bit for us. Instead of an acceleration or a deceleration along a straight line, now all of a sudden we're going to think about an acceleration as a change in the direction of something's motion, a change in the direction of its velocity. Okay, and so that's still an acceleration. If you remember back in chapter 3, one of the last things we talked about was a centripetal acceleration, and now forces cause centripetal accelerations. The speed may not change at all. In fact, if we say it's uniform circular motion, the speed doesn't change at all, but the direction of the velocity vector changes, and that is an acceleration. And it's as simple as many physics equations that you should start with are just a 3-term equation. The centripetal acceleration is the velocity squared over the radius. Okay, and then we had 2 definitions: the period, the time it takes to go around one circle, and the reciprocal of the period, the frequency. And then, of course, figuring out what that velocity is, well, that's the circumference of the circle divided by that period. Okay, and so those are just 3 of the equations that you're going to need. In some places on the worksheet today, I put those equations in, and you don't need to memorize them, but you should become familiar with them, know that they exist. All right, if I could, I'm going to shift gears here and share my screen with you. And all right, I don't see the green border, so let's make sure. Try it one more time. Oh, it went to desktop, that's why. Go to PowerPoint. There, now I see it. So you're seeing my screen with my little chicken scratches drawn with my mouse here. And this is the conical pendulum. And you can see this ball, this blue ball here, is constrained to go around in a circle. And like every Newton's second law problem that you're going to do through the entire course, the problem starts with doing a free body diagram on that ball. And so you can see there's the tension in the string pulling up and to the right, and there's the force of gravity, weight. I stole this diagram from another textbook where instead of using T and W, they use F sub T and F sub G, and you'll see that in various sources. Anyway, those are the 2 forces. The very first thing that had to be done, since the tension is off at an angle, was get the 2 components of tension. Okay, and hopefully you can see from 2 parallel lines, 2 vertical parallel lines cut by a transversal. This was a 10th grade geometry theorem I had to learn. Alternate interior angles are the same. So although theta is given up there at the top with the chord and the vertical, it's the same angle down here, closer to the tension force on the object. And better technique would be to completely divorce these vectors from the physical diagram, but we'll go with it here this morning. And so the dashed lines are the 2 components. The adjacent side takes that tension and multiplies by the cosine. The horizontal is the opposite side. That takes the tension and multiplies by the sine of that angle, theta. And then we look and we go, is the ball moving up and down in the y direction? And the answer is no. And so it's an equilibrium in the y direction. And so that means the sum of the forces in the y direction are 0. The tension times the cosine of theta minus the weight has to be equal to 0. And when I did the work here, I flipped over to using our book's notation. I went with T instead of FT. And weight is just mass times the acceleration due to gravity. And you can see right away from that, if I know the mass and I know the angle, I know what the tension in the string is. But even if I don't know all those things, I have an expression for the tension. And sometimes in physics we'll say, hey, what is the tension? And you don't have all the values. And an expression is a perfectly acceptable way to answer that. Let's say I didn't have the mass here, because as you'll see in a second, the mass is going to cancel, right? So I can say, okay, what's the tension? You just tell me whatever the mass is times g divided by the cosine of theta, and that's a perfectly acceptable answer. Every answer in physics doesn't have to be numeric. And in fact, many of them don't need to be. It's a more sophisticated form of learning if you can work symbolically. And then at the very end, you plug in your numbers when you finally have what you need. Anyway, so what you do, though, is you look at the horizontal direction now. And in the horizontal direction, that horizontal component of the tension it is pointing towards the center of the circle. It is what's causing the centripetal acceleration. And so the top line, the sum of the forces, our recommendation is let's make that the x direction. The sum of the forces in the x direction, well, there is only one, tension times the sine of theta, and then it's equal to the mass times the acceleration. Okay, this bit of math right here happens over and over again in circular motion problems. Okay, there's always something that causes a force that causes centripetal acceleration. Okay, now people term that a centripetal force, but a centripetal force is not a force in our catalog. And I normally don't lecture a whole lot on technical details, but this is one that is a misconception people have. Centripetal force is what causes that thing to go in a circle. Well, that's not the answer to the question. The question is, what is causing the centripetal force? In this case, it's the horizontal component of tension. If you're in a car and you're going around a turn in circular motion, that centripetal force could be supplied by maybe the tension in your seatbelt, the friction between your seat and your car and your seat. That could be causing the centripetal force. If you get kind of smushed over so your shoulder is hitting the door next to you, it could be the normal force between the door and your shoulder. Any one of those things in our category could be causing the net force, which is causing you to actually go around in circular motion. It's providing a centripetal force for you. And of course, without it, you continue going on in a straight line. So these are necessary things. Anyway, the algebra next is the next couple of steps here. I substitute in the tension I got from the y component, this is the y component of force being equal to 0, into the x component. And you see all of a sudden it doesn't matter what the mass is because it cancels. And I can figure out exactly how fast this ball is going with a little bit of algebra. And the only thing I would add to this problem is we're given the length of the cord, and the centripetal acceleration is v squared over r. Don't just go picking whatever length you're given in meters in the problem. You have to convert the length of that cord right here to the radius that you need. And of course, there's another bit of trigonometry that causes you to be able to find what that radius of the circle that the ball is going in. It turns out to be L times the sine of theta, because the radius is the side of a right triangle that's opposite that angle theta. Trigonometry, it's in this problem twice. All right, so that's kind of the quick overview of what was in the video last night. I do exactly the same math. I literally cut and pasted my work from the previous slide. I just changed from the tension in a cable, I changed over to a lift. Now, did I hit the record button? Yep, I am recording. Good. I had a senior moment there, forgetting if I hit the record button. I stole this diagram of an aircraft, which I find interesting because it's exactly the same thing that makes that ball go, that tether ball go around the post, is what makes an airplane turn. I don't like the diagram I stole in the sense that they're only showing the horizontal component of the lift. They're not showing the vertical component, okay? And again, once you've got the two components, well, you don't need the lift vector anymore. And you can see, just like in the previous example, L times the sine of theta, that is the unbalanced component of the lift, which causes a centripetal acceleration, v squared over r, ma right here, okay? In the vertical direction, exactly the same thing happens. Instead of tension, it's lift times the cosine of theta minus the weight. If the plane isn't ascending or descending, if it's staying at a constant altitude, the sum of those forces are 0. And that's the pilot's job to make sure that happens. So you can, again, solve for the lift, okay, from the y component, plug it into the x component, cancel the mass, and oddly enough, you get exactly the same equation for what the speed of the aircraft must be. And I could work the other way. I could give you the speed of the aircraft and ask you what the radius of its turn is. Or I can talk about the bank angle and let you figure out what the speed and the radius are, things like that. So the thing I do want to point out, though, is an equation like this isn't how you start this problem. How you start this problem is a free body diagram. Again, poor technique here because I drew it right on top of the physical diagram. But as you get more and more experienced, you can take that shortcut. Sum of the forces in the x and the y direction, algebra, final result, and at this point you plug in numbers. And that's the royal road of physics problem, Newton's second law type. Okay, numbers finally down here. All right, any questions on that? Excellent. Yeah,
I had a question about
yeah.
an earlier problem that you
Sure.
did. So you did a banked problem,
Yeah,
where
yeah,
a car was, like, on a bank,
yeah,
road,
yep,
and there was no friction in that scenario.
exactly.
Why did the friction go away?
It just to make the life easier for you. In reality, if you're getting on 301 maybe over by Chestertown, and somewhere Centerville maybe, and you go around a turn like a cloverleaf to get on, those are cloverleafs, but you know what I'm talking about. You get on a cloverleaf. In reality, you have both friction and a bank in order to help you make that turn. And this problem took away the friction, so that might be what you would experience in the wintertime when there's ice on that thing, right? And the only reason it was done is for simplicity and calculation. In reality, you have
Okay,
both. In real life, on a nice warm summer day, like where the road is dry, you'll have both friction and the bank to help you. Okay.
okay, thank you.
Yeah. No, only to make the calculation simpler. In reality, you would have to do both. You'd have to consider both friction and the bank of the road. But again, I think if you missed her point, um, let me find that slide real quick. Okay, that was with friction. See the free body diagram up here? Okay, friction pointing in, that's with just friction. And then we went on to the banked example, and now there's the free body diagram, and now a component of the normal force, in this case, is causing the centripetal force and causing the car to go around in a circle. And we just went, it's one or the other in our two models here. All right, good stuff. I'll move on here, ask a couple questions. Any others? That was a good one. No particular reason. Now, this car right here, is actually going around in a circle. It almost looks like it's going over a bump. That's just a poor diagram, but I'll launch the poll here, and hopefully from what I've been babbling about, this is pretty straightforward. Is there a net force on the car as it goes around this curve? Yeah, this is an easy one. This is the warm-up question. Yeah, everybody that's in so far is getting it right. 19 people in, and look, we're up to 26 already. Great. 20. All right. I'm going to cut it off because we've got a majority view here. 21, 4 people we're waiting on, 5 people. Nope, we're going to end it. All right. And the answer, of course, is yeah, there has to be. There has to be a net force that can create the centripetal acceleration v squared over r. If there isn't, what happens in a car? Well, Newton's first law kicks in. No net force, continues to move at a constant velocity or zero velocity, a special case. Okay. In this case, it would be a constant velocity. So yeah, the B is absolutely the correct answer here. All right, we'll move that over to here. Get rid of my little template here. And related to the question somebody just asked me, so hopefully this is pretty easy now because that was a good question. Why are many racetrack corners banked? All right. All right, 2 more people, but I'm going to cut it off here. We'll end it and I'll share it with you. I tell you, the reason I do these polling questions is it tells me if I was clear in something I just said. Apparently, I wasn't clear. Um, the question was when we talk about the bank roads, how come we didn't consider friction? And the answer is just to make the problem simpler. Okay. The 12 people who picked C here, you got it exactly right. The normal force can contribute to the centripetal acceleration, contribute with friction. In any real problem, both of them are there. You don't necessarily want friction forces. Okay. Uh, in fact, if you're a race car driver going around a turn, You're actually told to accelerate, oddly enough. It kind of squats your car down and helps get a normal force that's bigger, increasing the friction force and decreasing the likelihood that you're going to skid. Because remember, if there wasn't friction, you would skid to the outside of the turn. Friction is helping you. The bank helps you as well. Both of those two things provide a force towards the center of the circle, which causes a centripetal acceleration. Okay, so C is the right answer here. It's the one. And the thing to remember, and I think I said this in the video, I've often thought that people should not be issued driver's licenses until they've taken a physics course like this one, so they know how important that friction force is. In the wintertime, when there's ice and there is no friction, the only thing that might help you go around a turn is a bank. And if the bank isn't there and you try to execute a turn, you're very likely going to keep going straight on the ice. I used to live up in Maine, and that was a problem sometimes. You try to go around a turn, and if there was ice at the intersection, you kept going straight rather than making your turn. And you need that friction to go around turns. It has to be there to provide a centripetal acceleration. All right, next one. Hopefully I was more clear that this problem will hopefully clear it up though. Stop sharing. Come on, go on to the next one. I'll let you think about it while I pull up the poll. Okay, and so you got this ball in a tube here, right? And at some point the tube ends after it goes around. Got ahead of myself here. I don't even know what I hit. Which way is the ball going to go when it leaves the tube? Yep, some people still not believing here. Three more folks. One more. All right, everybody's in. Okay, the majority gets it here. For those of you who think B, my question would be why? All right, so I've drawn the ball in three positions. Here it's still going around the curved path, right? Why? Because there is a normal force from the outside of the tube pushing that way. Same thing right here. There's a normal force, just like you would have if you went around to curve your shoulder and the door, perhaps, are providing a normal force into the center. Right here, same thing, normal force, all pointing towards the center of the circle, causing the ball to go around. When the ball gets right here, what forces are acting on it? Well, there's no normal force anymore. And so there is no net force making the ball go around a turn. It goes straight this way. If you ever watched a hammer thrower in track and field, you'll see as soon as the hammer is let go, and so the hammer no longer has the tension to the hammer thrower's arms, what direction does the hammer go? And the answer is straight away from that hammer thrower's circle, right? It doesn't go through a curved path when he lets go or she lets go. Do women do hammer throw? I don't even know. There's another type. There's an indoor hammer too. Same principle. You swing it around, make it go around in a circle. You let it go. It goes off path C right there. Okay. Practical physics in track and field. Questions on that? Yeah, this one concerned me. The first people in immediately saw it. I think if you think it's B, my question for you would be, okay, well, what force is causing circular motion? There always has to be one. And if there isn't one, there is no circular motion. It's just that simple. All right, next one, and I think this is the last one. This is the physics of amusement parks, which is always fun to talk about. All right, where's my cursor? Right there. And I don't know if you've ever been in one of these where you're going around in a circle, in a cylinder, and it goes faster and faster and faster, and then eventually the floor drops out. And all you and everybody else is just going around in a circle in this thing. And so the question is, why don't you fall? What's the free body diagram look like? Why are you going in a circle and why aren't you falling? Yeah, disappointing. 3 more people. One more, just about ready to end it here. This one's a little interesting.
Dr. Tukolsky, I have a question regarding the last question that we had.
Okay. Let me end this, and before we talk about it, we'll go back. So what's the question on this one?
So in the video, one of the videos we had to watch last night on mastering,
Right.
they had 3 cans lined up.
Right.
And it hit like that middle can. So
Yeah,
why would that not be the B pad?
Yeah, no. Here's why. I almost pulled that video from y'all because I didn't like it. If you look at the way that his was oriented, and if that's what caused you to get it wrong, I should have pulled the video. If you looked, his tube went like this. Okay.
Okay.
And so straight ahead for that video, hit the middle can. The can that was over here that was C in this one, the thing would have had to come out and turn that way. And then of course the other can he had positioned went that way. And so his tube went a little bit longer, but when the ball came out of the tube, it was pointed right to the middle can. Okay.
Okay.
All
right. Thank you.
Question. Yeah, I didn't like it either because of that. It gave for me, it gave the wrong impression just because he wasn't very specific about pointing out where his tube ended as compared to where mine ended. And if that's the reason you got the problem wrong, but you still understood that once it leaves the tube, it goes straight, then you're okay. All right. Thanks for pointing that out. I'll think about that if I ever teach again, pulling that video. All right. Let's go back to the next one then. And I'll share the results with you. And it was a little bit disappointing here for me because apparently we haven't made it clear, but this circular motion stuff, it is a little difficult. Hopefully you recognize in each of these, that's the weight, right? I'm hoping even though unlabeled, everybody can see that's the weight, okay? And I guess the person isn't falling, right? What keeps the person from falling? And the answer must be a friction force. And since the person isn't falling and C and B here don't have a friction force, they really can't be correct, right? C could perhaps work, except there's no friction. This person will be falling downward because of the weight. So this is friction pulling up. And so now I think we're down to A and D, and most people pick D, but this would be, I guess, the normal force here of the person on the wall. That's not what we're looking at. We're looking at the free body diagram of the person. Okay, there's the wall, there's the surface pushing that way. So the normal force is right there. And if you look, that's exactly the direction the normal force needs to be in order to cause centripetal acceleration. So for the two of you, 2 people who picked A, you nailed it. Exactly right. Okay. That this wouldn't account for an acceleration that's towards the center of the circle. Okay. I need it to be that way. So there's kind of 2 things going on in this problem. The effect of friction, keeping the person from falling to the bottom when the floor pulls away. And then there has to be a force towards the center of the circle. And that's the wall, the cylindrical wall behind the person pushing towards the center of the circle as you go around. That would be analogous to your shoulder and the car door as you go around the curve. Okay. Only in this case, it's on her entire back. Questions on that? I'm a little concerned about it, but we'll move on. All right. Hey, we've got about 20 minutes left. And as I always do, I'll stop sharing this. I've got 3 problems prepared. I'm going to divide into 9 groups. And I think group 1, you get the one that was in the video, so you may have already seen it. Let's see. I want to share Acrobat with you. I give you some advice in the worksheet today on the equation you need, okay, to get a velocity, what the centripetal acceleration is, things about doing your free body diagram. N2L is Newton's second law. Remember your acceleration, force equals mass, net force equals mass times acceleration. The acceleration we're going to use is velocity squared over r, okay? And the first group, I guess 3 groups, you'll be doing this problem. This is a horizontal problem. Static friction is making a car go around. You just have to repeat, similar to a problem I did in the video last night. Okay, so that'll be groups 1, 2, and 3 when I divide you up here. Groups 4, 5, and 6, you're going to be doing the tether ball, which is that conical pendulum is what I titled it. It's just a tether ball. And so look at the tension and the weight, find the tension components, and set them equal to either 0 or mass times acceleration, where acceleration is the centripetal acceleration. And then the last group, you get the fun problem with the aircraft. Lift is a force. If you're troubled because it's not in our catalog, consider it like thrust or maybe even a normal force from air. And I know every aerospace engineer out there is going to cringe when I say something like that. We'll talk about how lift is developed. It's actually a pressure force when we talk about Bernoulli's equation, probably around Thanksgiving time when we'll talk about that, but it is just a force. Okay, so one thing people say I don't have a whiteboard. I've just offer a technique up for you, and I'll stop sharing this and share with you I opened up a Word document. I think if you don't have Canvas, you have the ability to get Canvas. If you don't have Office 365, as a student at Washington College, you have the ability to get it. I suspect most people have it. Anyway, if you notice, I've got the draw menu, and it gives me a little pen here, and this is obviously shareable, right? And that's with my mouse. I got to tell you, I've got a trackpad. It's a little harder for me with my pad, but you can still make words. Okay, and so if you're at a loss for a whiteboard, because we did find that if you work in the whiteboard in Zoom, when we disband the group and come back together, evidently that whiteboard needs to somehow be saved. Yeah, unless somebody knows of a way to save it. Question out there?
Yeah,
Yeah.
so if you're on a Mac and you want to save it, if you hit Command-Shift-4, it lets you
Screenshot it.
Yeah, select the area.
And there is a similar key on a PC that'll let you screenshot it as well. And so when we come back together in about 15 minutes from now, if you want to be the group to get 5 points again today by presenting a solution, that's what we'll do. All right, so I'm going to, where's my groups? Up. All right. Where is breakout rooms? There they are. It's in the menu. Okay, so I'm going to make 9 rooms here. Create the rooms. Okay, room 1, Kristen, Shanice, Tommy, Bridget, Nina, Mr. Wang, and you're going to have to tell me how to pronounce that, Mr. Wang. And then group 3, Ellen and Rachel. Okay, and so you guys will go off and do problem 1 with the friction. Room 4, Aiden, Shenyi and Sean, Elena, Jackie, and Jaleel. And 6 is Anna, Cora, and Kyle. You're doing problem 2. And then the last 3, Allison, Megan, Michael, Emma, Olivia, Andrea, Maddie, you're in group 7, 8, 9, and you're doing problem 3. So off you go.
Is this worksheet 6-1?
Yes, it is.
Okay.
Worksheet 6-1. Yeah. All right. Have fun. See you in about 15 minutes. Where are you at, you? Okay. I need to go to mute, so I just put them off the breakout. Any sign of the guys? They're out there? Anything out there? Anything they need? Put me down my flip-flops.
Dr. Tukolsky? Dr. Tukolsky?
Yeah.
I wanted to know if it's possible to just join a different breakout group because the people I'm with don't want to work with
Okay.
anybody.
So let me find you here.
I was in 2, I believe.
Gotcha. All right. So we'll move you to with Ellen in 3. Yeah, you'll still be doing the same problem, just working with Ellen and Rachel. Although Rachel said sometimes she's got noise problems, so she might help you.
Whatever.
All right.
I started it. It's just like it's hard for me to like focus if it's just like,
Yeah. All right. Well, it's free body diagram, sum of the forces. You should
Yep.
be moving here. Go ahead.
uh,
Not joined. It's probably just a time lag here. Yeah, you should be in group 3. Ellen will be there with Rachel. Although
all right.
Rachel sometimes doesn't like to talk, she told me.
It's okay. I'll try to join and see what happens.
Okay. Yeah, you're not moving.
have a quick question.
Sure, go ahead.
So I was looking at my work so far, and you know how like when you draw the components for the x and y directions for the ball,
Right.
for the x you get tension times sine of theta equals mass.
Times the acceleration.
Yeah.
Yep.
And then for the y you get tension times cosine minus the weight, or mg, equals 0, right?
Check. Yep.
So then the tension would equal mg over cosine. So could you solve for tension using that, or do you proceed to?
You could. Yeah,
Okay.
I forget, let me read the problem. Do you get the mass?
Yeah.
Yeah, so you could right there. Yeah, I did it that way too. So what do you get for your mass? I'm sorry, what do you get for your tension then?
I haven't gotten to that step yet. I just wanted to
Okay,
make
but
sure.
yeah, you could right there. You've got enough numbers in this problem statement, so you
Okay.
know what the mass, you know what g is, you know what the angle is, so you could get the tension right there, and then use that to figure out what the acceleration and the speed are. Absolutely.
Okay, thank you.
You bet.
Hello.
Anything I can do for y'all?
We actually finished the problem.
Okay. So what? Let's check your numbers. You can present again. What'd you get? Let's see. Your group 7. No, your group 8.
5.
Yeah, and Michael,
Oh,
is that why he left? Look at that.
Yeah. Yeah.
Okay, so about 2.6 kilometers. I agree with that. And did you have to get the, nope, just 2.6 kilometers. All right, you guys are ready. You can go back to the main room then. I'll be closing out the rooms here in just a second. Looks good.
Okay. Thank you.
You bet. Anything I can do for y'all? Sorry, you're the last group, so you're the last one I'm getting to finally.
No, I think we're good.
All right, then I'm going to close all the rooms and we'll see you back in the main room. Why won't this go away? All right. like we got most people back. Hey, anybody, I know I saw one group that has a good solution. Do you guys want to present that, show everybody else? They had a good solution to problem 3. And that was, I
Yeah,
guess,
we can do that.
yeah, if you, you should be able to share your screen. Go ahead and show everybody what you had there. Okay, make sure this is Allison, Michael, and who else was in this group?
What
Again,
problem is this?
Megan,
Yeah, it was.
Megan,
What problem
Allison.
is this?
What's that?
What problem is this?
This is number 3. Okay,
Got
so this is the jet. Look at their free body diagram. You can see the lift and the force of gravity. And they found the 2 components. And go ahead, you guys start talking. Somebody, Allison, your screen, you can go ahead.
so we found the lift components, and the only thing in the x direction is the x component of the lift. And then that's equal to the acceleration, because the acceleration in the, like, that's the only force in the x direction.
Right.
And then, so that's where we found this here.
Right.
And then with the, this one, the force of the lift in the y direction is equal to the force of gravity. So that's where we got this equation. The force lift is equal to mg over, and then cosine 37 is just part of the component for the y direction.
Yeah, and I want to point out something real quick. You're doing great. In group, the problem 2 people, I got asked, I think Jackie, you asked me, could you just, in your case, it's not the force of the lift, it's the force of tension. And at this point in the problem, you know the mass, you know G, you know the angle. Jackie asked me, can you just calculate the tension right there? And the answer is yes. In this problem, I don't think we tell you the mass of the aircraft, unfortunately. So it's slight difference in the problem. But group 2, problem 2, you should have exactly the same line, only it'll say tension is equal to mg over cosine of theta. Keep going. Sorry to interrupt, but it just want to make sure group 2 sees how it applies to them.
All right, and then we did, we took this equation with the force of the lift, and then what the acceleration was, and we put them, like, we plugged in the force of the lift in the acceleration equation, and then we got the gravity times the tangent of theta is equal to the velocity squared over r, and then we found that our radius is 2.6 kilometers.
Yeah, so once you start putting the numbers in, you're just going to your calculator. Does that say 13?
No, 139.
139, gotcha, squared. Okay, because that was, yeah, you had to convert from 500 kilometers per hour to meters per second, and that's what the 139 is. Okay, good. Any questions from anybody else? Problem 2 people, pretty much exactly the same, only substitute out lift for your tension in the cable. Problem 1 people, you're doing exactly the same thing, only instead of a component of a lift or a component of a tension, you have a horizontal friction. Okay, but the problem is solved precisely the same way. All right, I think I'm going to change my directions. Thank you. Make sure I got who's in that group. That was Allison was presenting there. Other 2 people in the group, and I'm listening carefully here. Megan and Michael.
Yeah.
Sounds good. Okay, you guys will obviously, you don't have to turn anything in. Everybody else has to turn in your particular problem, either 1, 2, or 3. And I think my directions on Canvas were not exactly that. I'll change them. So if you were in group 1, you're turning in problem 1. If you were, so that's group 1, 2, and 3. If you were in 4, 5, and 6, you're turning in your problem 2. And 7, 8, and 9, you're turning in problem 3. And of course, Michael, Megan, and Allison, you've already turned it in. I just graded it while you were showing everybody else. Hey, have a good weekend. Any questions for me? You guys have fun. Take care.
Thank you.
You bet.
I have a quick question.
Sure, go ahead. I'll be hanging around here for a little bit.
So I got the tension for my question. I got 4.8 or 5 newtons.
Hang on, let me check that number. That sounds, I got 4.8 as well. Yep.
So I'm trying to stop with the velocity now.
Yep.
But I don't know the radians. I mean the radius.
Yeah.
Yeah. So how would I find the radius?
Yeah. Okay. Let me share my whiteboard with you. Whiteboard share. And hopefully you're seeing my whiteboard.
Yeah.
And so you do know the length of the cable though, right?
Yes.
And that's 2.7 meters.
Correct.
Okay, and you're looking for the radius, which is the distance from the pole, right?
Mhm.
There's the pole. And you know this angle right here is 35 degrees.
Are you drawing on the whiteboard?
I am. You're not seeing it?
No.
Oh, it says it's paused for some reason. Let me stop sharing and reshare my whiteboard. Hopefully it'll still be there when I get back.
Yeah. Okay.
Okay, see it right there? Yeah, you know what I did? I have two screens up at once. I grabbed it from one screen, put it on the other screen on my computer, and it lost it when I did that. All right, so anyway, so the 35-degree angle up here at the top, and the cable right here to the ball or cord or whatever is 2.7. And so you see you got a nice right triangle right here.
Yeah.
And so this is the radius that you're looking for. I think that radius, let's see, it's the opposite side of that 35-degree angle, right? And so that would mean I'm using the sine,
Correct. Okay.
right? So just take L times the sine of theta, and that should be R. Okay.
Okay.
Yeah, one more step. You had to calculate that because we didn't give it to you. All right.
Thank you so much.
All right.